and today we're going to talk about the multiple ways that one can use to increase the rate of chemical reactions. So let's jump right into it. The first way to speed up a reaction is to increase its concentration. Okay, so I'll make a box here to represent our container holding our molecules. Let's see. There, that's our box. And we're going to put in some molecules. Here's about 4. Now add some different molecules, our other part of our mixture here. About 4 of these as well. Okay. Now I'm going to draw a box right over here that represents a higher concentration of these molecules. So we've got our red now. Put in some more. This will represent our higher concentration. So if you notice, I'm making a lot of molecules. And done. Okay. So, all right, so now we have our before and after pictures of this reaction. Is there anything you notice about this? Well, using our trusty tool of observation that we possess as scientists and a little common sense dashed in, we can tell that the molecules are a lot more tightly compact and that there's more molecules in our after picture. Now, in reactions, when molecules make contact with one another, it helps in speeding up the reaction. Naturally, if these molecules are pushed together because there's a lot of them, then they're going to collide more often, which therefore speeds up the reaction rate. Okay, so an analogy in the real world, or at least in a sense that's more relatable, we're going to look at this picture here of a large crowd of people. They're really close together and there's a lot of them. Most likely these people will be bumping into each other quite frequently. After all, there's not much space to move. This relates back to increasing the concentration of our reaction. These people represent molecules. They collide when there's a lot of them in one space. Now moving on to our next means of increased reaction rate, an increase in pressure. So take a look at this box I'll draw right here. Let's see. It's a nice, big, airy box. Plenty of room for our molecules. See, and they're kind of far apart, our molecules are. There we go. And now I will draw a bigger, and actually a smaller container here. The one who has had pressure affected. We will draw our green ones. There's about 3 of each, as you notice. So it's a more constricted space. See them? They're all together. There. And so the original container and the smaller container are represented here. There's the same amount of molecules in here, 3 greens and 3 blues, but there's less space for these guys to move around in. They're now going to collide more because they're forced into a smaller area that is not so easy for them to avoid one another in. The analogy for this one is represented by this kind lady and gentleman that are currently sandwiched due to a lack of space between airline seat placement. These 2 people perhaps went on a different airline are not lacking space at all. They both have plenty of space and can easily evade any unnecessary contact. However, when putting them in an airplane with less space between seating, they're forced to make contact with one another, similarly to the effect of increased pressure on molecules. Now, increasing temperature. I'll draw a box here that is cool. Let's see. Here's our cooled box with molecules in it. We should put this here. And see, and these molecules here, they're moving very slowly right now because they're cool. And cool molecules move a lot more slowly than that of heated molecules. So we'll label this cool. All right. Now we'll come right over here and make us a box of the same size, approximately, and make heated molecules. Make the box heated. Let's put this here. There, we got the same amount, if you notice. 4, just like we had in our previous one, and 3 of the purples. There we go. But see, the thing that's different about this, let me put heated. Heated. The thing about this one is that the molecules are moving much more rapidly. See, here's some lines. They represent our rapidly moving molecules. And so they just bounce all over the place, you know. Just very, very rapid movement. And so with the heated box, the molecules move faster. When molecules move more rapidly, there are more collisions that occur, which therefore increases the speed of the reaction because they're bouncing around off the sides of the box, and they run into each other. Now, the analogy for this would be a snake. Snakes change their speed of movement depending on the temperature. When it's cool, snakes are not able to move very fast. They're cold-blooded, so it's more difficult to move in cooler temperatures. However, when the temperature is higher, snakes can move much more easily. This is similar to increasing the temperature of a reaction since molecules can move faster when there's more heat. Now, increasing the surface area. Okay, I'm going to draw a box here with some cube-shaped molecules. Let's see, maybe red this time. Let's see our cube. I'm going to do about 2 of each. There we go. And do a yellow one. Let's see. So what you're going to notice here in a minute when I do the next box that has an increased surface area for each of these. It's right over here. It's the same size of box. You know, the size of the box doesn't change. But what you'll notice is that the molecules will break apart. See, they make smaller pieces. Little bitty facsimiles of this right here, of these bigger molecules. See, they make little bits and pieces, which is increasing the surface area. It's allowing more of the area to be eaten up, reacted with as we go. It's just much faster than having these large cubes to have to consume in our reaction. It makes these smaller ones instead. Here we go. Makes these tiny little molecules. All right, so the surface area has been increased because, as you can see here, the individual large cubes have been broken into smaller pieces. This exposes more of the area of the molecule to be reacted with, which therefore speeds up the reaction. Now, the analogy for this one is a bulldozer pushing down trees. This bulldozer can be tearing down the trees for a variety of reasons, but most likely it's making an area for a building or maybe even a park. When more surface area of the land is exposed, there is more room to build a structure, which relates to the concept of increasing surface area. There's more land to build on. Now for a catalyst. This is our final way to increase speed of reaction. Now, I'm going to draw a graph here. This is the best way to represent this. So we have our Nice little graph. See, this is our flat part. And this would be our normal activation energy. See, the activation energy would be the energy required to undergo a reaction. See, and if you notice, this right here is our initial activation energy before the catalyst is put in place. See, this is initial energy. Give me a second, I'm kind of slow with my writing here. There we go. Our initial energy. All right, so when we use a catalyst, it reduces this amount of energy. And what you're doing is that you've got instead here, it's going to, this is our catalyst here. See, it reduces this significantly, and it increases the speed of this reaction because it reduces this activation energy, like I said. When there's less energy required to perform this reaction, the reaction rate is sped up, as you can see in the graph. See, I mean, it's a lot faster. I mean, it's a lot less energy required, so you don't have, and it doesn't take as long. The analogy for this would be a car. When a person is in a car going somewhere, perhaps to their workplace, it is much faster than getting to the location on foot. The car reduces the time to reach the place that you are trying to get to. This is like a catalyst because similarly to the vehicle, the catalyst lowers the amount of time for the molecules to react. So what have we learned? Today we learned about the many ways in which to speed up a reaction rate. Thank you for watching.